Hello students, this is a beautiful JEE Advanced problem from 2017. What we have here is a disk which is moving with a speed v through a gas. The question is, what is the resistive force exerted by the gas? And the question is actually a one-dimensional problem because we are to assume that the gas molecules move only left and right. They don't have a y component to the velocity. Also, all the gas molecules move with the same speed u, which is much greater than the speed of the disk, which is v. Now what I'm going to do is place the question in front of you, and what I would like you to do is pause the video, attempt the question, and then resume the video and take a look at the solution. Good. Now let's look at the solution. Let the area of the disk be A, and let N be the number of molecules per unit volume which are moving to the right, and N is also the number of molecules per unit volume moving to the left. In other words, the total number density is 2N. Alright, now look at this. Let's first find out about the collisions coming in from the right. Let's take a look at these molecules. A molecule which is moving away from the disk is not going to collide with it because it's moving much faster than the disk. So only the molecules moving towards the disk will collide with the moving disk. So how do we find out the momentum transferred by a molecule of mass m when it collides elastically with a moving disk? To answer this question, let's go back to a classic old problem. The problem is this. There is a wall and a tennis ball is moving at speed u and collides elastically with the wall, but now the wall is moving. Now, suppose the wall was stationary, we know what happens. The tennis ball goes, hits it, and bounces back with the same speed u. But now the wall is moving. So how do we solve the problem? So it's very simple. We know what happens when the wall is stationary, so get into the wall frame of reference. In the wall frame of reference, the wall is stationary and the ball comes in now with the velocity u plus v. Remember, in the wall's frame, the ball is now coming faster because the wall is moving towards the ball. So the ball is now coming with the speed u plus v, so it bounces back with the speed u plus v after an elastic collision. So the returning ball has a speed u plus v in the moving frame of the wall. So seen from the ground, the velocity of the returning ball is u plus 2v. It's easy to see that if a train is moving with speed v and inside the train somebody is rolling a ball with a speed u plus v, then seen from outside, the speed of the ball is u plus v plus v. So u plus 2v. So we get the nice result that a moving wall will deliver an extra 2v speed to the returning ball, where v is the speed of the wall. Now we have all experienced this. Every time you hit a ball with a tennis racket, the tennis racket delivers twice its velocity to the returning ball. Or if you hit a cricket ball with a bat, the bat delivers twice the bat's velocity to the returning ball. So the faster you move the bat, the greater the speed with which the ball takes off after it collides with the bat. Now the same idea is used in the slingshot effect problems. In the slingshot effect problem, in one dimension, this satellite which far away from this planet has a speed, let us say, u, and it's heading towards this planet, and the planet itself has a velocity v to the left. It's exactly the same problem. You go through the same arguments and you come up with the answer that when this satellite finally swings around the planet and goes back, when it is far away, it now has the speed of u plus 2v. Now this is called the slingshot effect, and it has been successfully used by both NASA and ISRO when they send satellites swinging around planets to pick up extra speed. Alternately, you can now imagine that if the planet were moving in the opposite direction, the satellite would slow down. So if I wanted to slow a satellite down, I can swing it around the planet moving in the appropriate direction. Likewise, if the ball were moving away from the incoming ball, the returning ball would have a velocity of u minus 2v. Now we are ready to come back to our disk. Let's take a look at this molecule and ask the question, how much momentum does it deliver to the disk? Let's take rightward is positive and left is negative. So the initial momentum of this molecule is minus mu. It collides with the wall that is coming towards it. When it bounces back, its momentum is going to be mu plus 2v. So the change in the momentum of the molecule is the final momentum mu plus 2v minus the initial momentum minus mu. So this becomes 2mu plus 2mv. If this is the change in the momentum of the molecule, then the change in the momentum of the disk is going to be minus of this. So the momentum gained by the disk is minus of 2mu plus 2mv. The minus sign tells me that when this molecule collides and bounces back with the disk gains a momentum of 2mu plus 2mv to the left. The minus says it's to the left. So the momentum delivered is 2mu plus 2mv per molecule to the left. Now, let's find out how many molecules collide with it per second. Now, these molecules which are moving away, we can ignore them. We only need to worry about these molecules which are moving towards the disk, and their density is n molecules per unit volume. To find out the number of collisions that happen during 1 second, consider a point, a distance u plus v from the disk. Now, all the molecules that are at this distance, which are moving towards the disk, will collide with the disk in 1 second. This distance is u plus v. During 1 second, the disk moves a distance of v, arrives here, and during the same 1 second, these molecules move a distance u and arrive here to collide against the disk. So the molecules move a distance u in 1 second, the disk moves v, so all the molecules at a distance of u plus v will come and collide with it in 1 second, which means that all the molecules in this cylindrical volume will hit the disk during the 1 second. Now, what is the volume of that cylinder? It's going to be cross-section area A multiplied by u plus v, that's the volume, times n gives me the number of molecules which collide with the disk in 1 second, and each one delivers a momentum to the left of 2mu plus 2mv. So we get the beautiful result that the force to the left due to collisions is going to be 2m a n u plus v the whole square. So this is the force acting from the right side. Let's look at the force from the left side. Now if you take a molecule here, now that's moving towards the disk with a speed u, and a molecule which is moving in that direction is not going to collide with it. So these molecules from the left which are moving to the right will collide with the disk. And how much momentum do they deliver to the disk? You can easily convince yourself that when they bounce back, they are going to bounce back with the speed of u minus 2v. Remember, v is the speed with which the disk is moving to the right. So these molecules are going to move away with that momentum. So you see, a molecule moving to the right with an initial momentum mu collides with the disk and bounces back with a momentum of minus mu minus 2v. Why minus? Because it's moving to the left. So final minus initial gives me minus 2mu plus 2mv. That is the momentum change of a molecule. So minus of that is the momentum delivered to the disk. The momentum delivered to the disk is 2mu minus 2mv per collision. Now how many collisions do we have per second? Again, we'll try a similar method. We'll consider molecules at a distance of u minus v from the disk. So these molecules will come and collide with the disk in 1 second. Let me give you a different argument now. Look at it from the point of view of the disk. In the frame of reference of the disk, which is moving to the right, the molecules are moving with a velocity u minus v, which means molecules at a distance u minus v will come and collide with it in 1 second. So again, we construct this cylinder and consider the number of molecules in this cylinder of length u minus v. Let's do that. So length is u minus v times the area A times n is the number of molecules moving to the right which collide with the disk, and each one delivers a momentum 2mu minus 2mv to the disk. So the total momentum delivered per second is 2m a n u minus v the whole square. We have our disk and there is a force from the right which is a resistive force, and that force is 2m a n u plus v the whole squared, and there is a force from the left in the same direction in which the disk is moving with the speed v, and this force is 2m a n u minus v the whole square. You can see that the resistive force is greater than the assisting force, so the net force is going to be resisting, and the net resulting resistive force to the left is going to be 2m a n u plus v the whole squared minus u minus v the whole squared. U squared cancels, v squared cancels. You have 2uv here plus 2uv, that is 4uv multiplied by 2. The whole thing is 8m a n uv. This is the resisting force. Let's call it R. R is the resisting force, air friction in this problem. So we have answered the question. Let's ask the question, what happens if I exert a constant force F in order to keep the disk moving? So if the disk starts from rest, F is equal to mass of the disk times its acceleration. So it accelerates to the right, so it picks up speed, and as it picks up speed, the resisting force R increases, which is 8m a n uv. So as the speed picks up, the resisting force increases. So at any instant of time, the net force to the right is F minus 8m a n uv divided by the mass of the disk is equal to the acceleration of the disk. As long as the force is greater than the resisting force, it accelerates to the right, it goes faster, faster. As it goes faster and faster, the resisting force increases until the resisting force equal to F, at which point the acceleration becomes 0. At that point where F is equal to 8m a n uv, the acceleration becomes 0, the velocity becomes constant. Once the velocity becomes constant, the resisting force doesn't change. We are not changing the exerting force F, so the net force continues to stay 0. So it continues to move with a constant velocity, and this gives us the terminal velocity. So if I wanted to know what the terminal velocity was, the answer is F divided by 8m a n u. You can see that if the cross-section area is larger, the terminal velocity is less, and if the number density is larger, the terminal velocity is less, and if the molecules are moving faster, the terminal velocity is less, which means if I heat the gas, the terminal velocity will be achieved sooner. Well, That's it, folks. I hope you enjoyed this JEE problem.